So welcome everyone. This is the creating an open source FMS during the COVID-19 lockdown, supporting off-season events for years to come presentation in class 2 for the second session slot. So just keep in mind that this presentation, including the Q&A, will be re-recorded. So make sure to keep your gracious professionalism in mind while interacting with this presentation. And so our presenters are ready to go. And without further ado, you guys are ready to go.
All right, good morning. My name is Terry Willingham, and I am the Executive Director for the Foundation for Community-Driven Innovation, which is the nonprofit that sponsors the Edgar Allan Holmes First Robotics Competition, Team 5276, and the MROC Fab Lab, where the FRC field, First Robotics Competition field, is located, where they've been working all summer on the development of an open source field management system. And the team's fantastic. We're really proud of them. They're going to tell you, a lot of technical stuff about what they did, but they worked really hard with the rest of the team, incorporated remotely on a variety of different aspects of the project. And it's really terrific. We're happy to answer any questions. They're happy to answer questions and help other teams implement this idea. And we really want to give them a big shout out. And without further ado, I'm going to turn it over to Chase and Nathan, and they can talk to you about what they've done. So thank you all very much.
So hello, I am Nathan Kutsan, and I am one of the programmers on Team Edgar Allan Holmes 5276.
I'm Chase McNell. I'm another one of the programmers on Team 5276. We've both been working on the Nevermore field management system here. So who are we? I'll take off my mask. Might as well. Everybody's 6 feet away. All right, so who are we? We have Nathan Kutsan over there. You can see his email there. And me, Chase McNell. If you guys have any questions about what we're doing here, or you guys want to get involved, you guys can send an email to either one of our addresses, or you can send one to Miss Terry. We didn't clear email here, but it'll be on FCDI if you guys want to investigate their nonprofit. So who's Edgar Allan Holmes? This is our FRC team. We're a 7-year-old team currently based in Amrock, Tampa Bay. We're a fab lab here in University area, and we're a full-blown robotics center. And we have plenty of programs here to help with the university area, which is a fairly impoverished area. And you can see right here our little robot. This is from the season. This is one of our earlier versions when we were trying to test out getting it lifting. Just a little photo. You gotta keep photos in here. Anyways, I guess Ms. Terry does not want to do a whole talk about this right now, so we'll move on to first field management system. So what is it? I already saw a question there about what it is, so this will answer your question. So basically, the field management system is designed to be the center of a first robotics competition event. It manages the event schedule, the awards, the scores, the actual matches that go on, but then it also manages actual robots on the field during each match. For example, if a FTA or one of the referees wants to disable a robot, it's through the FMS that they do that, or through one of the referee panels. And also, it manages the timing of that actual event, sending you whenever you're going into autonomous period, just regular stuff, and also disables you during any times that you should not be going. So it also maintains a level of safety within that, which, as we mentioned earlier, referees can disable you, and also the FTA can manage you guys and watch what packets, watch how your network is going and whether or not you may or may not be trying to cheat. So why an alternative FMS? So the first FMS is completely proprietary. There's no open source software that's from the FMS side of first. It's really hidden from the community in a lot of ways. And also it's very, 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 very expensive, as some people may know. And an alternative and open source FMS also will give students and teams really an opportunity to be involved in production level networking code. So production level networking will be something that really a lot of people would love to get into, and it's something that's very hard to get into because it's really complex. It involves a lot of low level things and also something that you're typically going to be taking a couple college courses on. we thought it would be a great idea to start this FMS both to learn a lot about using networking and to help other people with this. And additionally, this year with whole coronavirus, we want to be able to have a virtual or hybrid event. So we don't want to have all the teams on site and like all queued up and waiting there, because obviously you don't want to have everybody in close proximity, because it'll everybody in close proximity without knowing who is there, but without knowing exactly who is beside each other at each time, because you want to be able to contact trace everybody. So this year, we were thinking about making it such that this FMS is designed for virtual events. So it's able to upload everything to a separate service, which would be managing that entire multiple different venues. And also it will allow for us to use non-traditional equipment, which would be the Rockwell Automation Centers. So the name of this FMS is called Nevermore FMS, a reference to one of Edgar Allan Poe's poems. Obviously, it's called Edgar Allan Poems. And it's a from-scratch implementation of the FMS protocol. It's written in a language called Elixir, which is based off of the ERLang virtual machine, which is a highly fault-tolerant and concurrent virtual machine. It's controlled by the GraphQL API that's implemented by React frontend that we're currently working on. And also, it's able to integrate with inexpensive and open source sensors to allow for us to have fields that do not have the thousands, or actually it's tens of thousands of dollars worth of sensors from Rockwell Automation. And on top of that, it's designed to be modular. So from year to year, we can easily just add in another event and not have somebody have to download an entirely new FMS for it and not be able to use previous years. So I'll let Nathan go ahead and talk about the components of an FMS.
Okay, so let's just go over the main parts of an FMS. And also throughout this presentation, we're going to kind of go into the technical details of just FMSs in general and specifically our implementation to sort of talk about the unique technologies we've used and sort of get people interested. So with an FMS, there's the networking hardware. So at its core, there's the core switch, which connects all other devices. That's going to be the access point, the router, and alliance switches. So a router is responsible for all of the firewall rules on the field. And that's to make sure, teams can't access other teams' robots. Teams can't access other teams' robots or can't access, devices that they're not supposed to access. And likewise, other, just making sure that whatever devices is on the network can only access what it's allowed to access. The access point is where the robots connect to. And then alliance switches, there's 2 of them, one for each alliance on the field, and that connects to each of the 3 teams' driver stations for that alliance. So the FMS computer is what runs the FMS software and the associated hardware stack and software stack as well. And it controls all the aspects of the FMS. And one of the most important parts is that it has the fail-safes needed for safety within a first field. And then we have the field sensors and lights. And so sensors on the field allow for automatic scoring along the field, and then lights and other similar things give visual feedback to teams and spectators about sort of what's happening in an event and during a match. And then you have control interfaces, so that's going to be your referee panels, the tablet that the FTAs carry, your scoring table, and just all of these different things are ways for administrative people to interact with the FMS. And so those are the core components of any FMS. And now we're going to dive a little bit into the technical details about FMS networking and how all the robots are connected, how the driver stations are connected, and that sort of thing. So I'm just going to briefly talk about this. If you're not familiar with it, this is the OSI model. It basically just talks about how there's low-level stuff, such as the physical layer, which is just electrical signals going through wires. And then you sort of build yourself up from that layer. So you have data link, which is the Ethernet layer, and then the network layer, which is your layer 3 protocol, which is IP, and so on and so forth. Most of the FMS lies on that transport layer because it uses TCP and UDP, which we're going to talk about in a second if you're not familiar with them. One other thing to remember as we're going to talk about this is what subnets are. So subnet in a network is a set of IP addresses that devices can connect to without having to pass through a router. They can essentially just pass through switches. If you ever have to access a device not on your subnet, you have to go through a router. And that is one of the main principles on the FMS, is that anything that's not right on your subnet, you have to pass through the router, and therefore we can have firewalls at that point. And one of the main things that the FMS employs is VLANs. So VLANs are virtual LANs or local area networks. And they are a way to have sort of separate networks, but use the same hardware, because otherwise you'd have to essentially duplicate a lot of hardware, which is just expensive and doesn't make a whole lot of sense. And so on the FRC fields, like I sort of mentioned before, each robot and their driver station and whatever other devices the team has is isolated. They're on their own separate network and they're on their own VLAN. So they can freely communicate with all of their own devices, but they have to go through the firewall to access the FMS, and then they can't access anything else. And so VLANs make that very easy. VLANs, just a brief overview, are essentially tagged with an ID whenever they go through a switch, and they can only exit through switches and router interfaces that have that ID allowed. And just as a visual example, you can see if we didn't have any VLANs, you would essentially have to have a central router and then 6 separate switches and 6 separate access points, one for each team running on the field at a First Robotics competition event. However, with a VLAN, you can see we only need 1 router, 2 switches for each alliance, and 1 access point, because then those switches and the access point can sort of differentiate who can communicate with who, because they're all separated with VLANs. Okay, and then one other thing about IP addresses on the field. Again, if you've never worked with First Robotics competition stuff, this is going to be pretty foreign. But basically, every single team at any First Robotics competition event has an IP address of 10. The first 2 digits of their team number, the second 2 digits of their team number, .0, and with the last number there being variable, so that any device connecting would use a different number there. So for example, our team is 5276. So our IP address would be 10.52.76. Some other number depending on the device. And this is how it is currently at all First Robotics competition fields. That's a specification made by First. The FMS is always at that IP address 10.0.100.5. Again, that's just something decided by First. And all driver stations expect that IP address to be there. And then the routers can allow all the teams to access the FMS, but nothing else. Even though since they're not on the same subnet, it means it has to pass through our router in order to get access there. So the FMS and driver station. So a lot of this stuff here is stuff made by First protocol. And so TCP and UDP are just 2 different general networking stuff. TCP is stateful, meaning you create a socket and then you have bidirectional communication, 2-way communication that is held through a port number. Whereas UDP is sort of one-off. You send your message and that's it. And you're not necessarily, it's not by the protocol that you're getting a reply. It's sort of whatever is implemented. As far as First is concerned, they use TCP sort of to get that initial connection with the driver station. That sends, for example, the team number and some other important information. But during a match, they use UDP to sort of give state information. And the reason is UDP is generally going to be faster than TCP. And since they're sending those UDP packets a ton, it's not necessarily a big deal if one of them gets dropped. Whereas with TCP, if one of them gets dropped, it's part of the TCP protocol that it gets resent until it gets there for sure. Okay. So let's just talk about the FMS protocol in general. And again, this is what First has implemented and how they've decided to do it. So as far as where we got this information, we got it from a great open source project called FRCture. And that's sort of one of the great things about open source is that we were able to find this and use the information from it. And when we had to do our own searching through a program called Wireshark, which allows us to monitor packets, we were able to contribute back to this project. So that's one of the great things about open source, and one of the main reasons where this FMS is also open source. But anyway, so the FMS connects to a TCP, sorry, the driver station connects to the FMS server, always at that IP address, 10.0.100.5 on port 1750. And this basically is the driver station telling the FMS, hey, I'm here. And it sends the team number along with that. And then if the FMS has decided, yeah, you're allowed to be here, then the FMS will start replying to the driver station with UDP packets every 500 milliseconds. If you've ever worked with an FRC robot or a First Robotics competition robot, that 500 milliseconds will seem familiar to you. That is the same rate at which your code loops on the robot, and that is where that comes from. It comes every single time the FMS sends a packet. And then so once we have that solid communication through TCP, UDP is what sends the wanted robot state, such as being enabled or disabled or emergency stopped. and other game data like what time is it in the match, how much time is left, and certain scoring information. So that one sort of depends on the game that's being played that year. Okay, so I'm going to invite Chase back over here to talk about Elixir, which is one of the unique technologies they've used in this FMS to make it extremely fault tolerant.
All right, I'm back, y'all. So now we get to talk about the interesting stuff, programming. So Elixir, it's basically, as I said earlier, a language that runs on top of the Erlang virtual machine. It's similar to how Kotlin runs on the Java virtual machine, in that it pretty much just compiles to its bytecode and is able to run on that virtual machine, and also able to take advantage of all the different technologies within it. So the code is split into what's called modules. This is a very familiar to functional programming, and especially Ruby, which is heavily what Elixir is based off of. And using those modules, you're pretty much able to define everything from GenServers, as we'll talk later, to just simple functions that you're going to be calling as a example, or sorry, as in how it is with a functional programming language, which basically means that you're calling that function as if it's in the state of that process. We'll get into that a little bit later. But so first off, we need to talk about the data types within Elixir. Basically, we have the integer, which is just a number with no fixed maximum or minimum size, which is big number arithmetic, which is implemented in a decent amount of newer dynamic languages. And then the atom, which is similar to Ruby, has a similar concept to this. It's pretty much a constant with the same value as what its name. And then booleans, which are the atoms true and false. I'm sure most of you guys would know that what true and false are and what a boolean is. And then a string is just a regular UTF-8 string. And a list is a linked list. And a tuple is basically Elixir's version of arrays, as in that they're fast in index and length, but not nearly as fast. Well, not able to grow nearly as fast as a linked list. So next up, we need to talk about processes. So in a lot of programming language nowadays, we would know about object-oriented programming. So we write everything as if everything is an object per se. Well, Elixir really puts that on its head, and because of its concurrency model. So its concurrency model is basically processes, and these processes are basically coroutines that are ran within a scheduler inside of Elixir. You can compare them basically tasks being assigned to a bunch of workers. So let's say you have a manager and a bunch of people that work underneath him. We could say 8, as in 8 threads or 8 cores, which would be the highest performance. So you would give every single one of those 8 people a task, and they would complete it, and then you'd have a new task and give another person that task once they complete the next task, or the task that they were doing. But why processes? Why does Elixir use processes? Well, first off, they're completely isolated. Unlike a lot of other programming languages, in which it is that your entire application will crash if you make one mistake, unless you do error catching. Elixir basically catches those errors automatically within the process and only shuts down that actual process per se. It's basically, you can think of it as a microservice architecture. Some of you guys may know that. That's used by most major companies and within the cloud. And also, and as I said, it makes it nearly impossible for the entire program to actually crash. So, for example, if a team is to send invalid packets over their TCP socket, the only thing that can actually crash is their driver station GenServer, which means that if they were sending invalid data, trying to cause some form of integer overflow, which technically is impossible on this, it would not work at all because of the fact that only their TCP socket will be disconnected because their TCP socket is connected to one process. And as I said earlier, it uses a scheduler across multiple different threads, which makes it dirt easy to use multiple cores. So how do these processes really work? As I said earlier, they're the exact same as coroutines. They're just tasks that get run inside a scheduler. And they're scheduled using what's called preemptive scheduling. So that's something a little bit unique about this. This is typically only used within operating systems and not nearly as much as our programming languages. But what it means is that whatever you're running can at any time be stopped and something else can be run during that time. So let's say, for example, you have like a constant loop that's running. but then something else comes up that has much more importance. It will stop that loop, run what's of more importance, and then switch it back to the other one. This is very hard to do with a lot of regular compiled languages, but thanks to the fact that this is a virtual machine reading bytecode, you can interrupt it fairly easily. I talked about that right there. And also, in order to be thread safe, which would be required because of the fact that it can be put across any of the threads that are created for the scheduler, they use what's known as messages. So you can think of them as like Golang channels, or Rustlang has a similar concept, in that it's pretty much you're sending messages between the different processes that creates a copy of it in memory and makes it such that you cannot have any issues with mutex locks. So we can talk about the GenServer. This is essentially an abstracted state machine based off of a process. So what you do is you would send a message to the GenServer, and then that GenServer will be able to run a piece of code, and then it returns the states back into itself. So then the next time something runs, that state that you set is going to be running along with that next function that you run or message that you send. You can think of it similar to regular networks, or even better, you could think of it as sending HTTP requests to a web server that you write. It's going to be running that code that gets sent that you defined for that certain path on HTTP. However, it will also be able to save the states within a GenServer, which is where it kind of differs a little bit. So the best way to explain it is really just show a little bit of example code. So here's an example of GenServer. We can see that it's within a large module that we define as nevermore.field.infiniteRecharge.driver station. We then import GenServer right here. This basically defines all the callbacks and different functions and helpers that will be needed in order to use it. And then the first thing we do is we define init. This is the function that gets run whenever you create that actual GenServer or the process that would run that GenServer. And then we have an input here, which you can define as anything. It's a regular function. And then we return the actual initial state that we want to have. This initial state will then be what will be shown in this state variable right here the first time it receives a message. But then if you were to modify the state within this code right here, return it, and you send another message, this state will have the new state. So it's pretty much just a state machine. And pattern matching. As we can see back here, we have an atom. So an atom is a constant. Well, how do you put a constant with an actual function input? That wouldn't make any sense. You can't set it. And most of our programming languages error out on that. So we have a constant called pattern matching Elixir. It's also an ER-lang, and that's where it gets it a lot from, but it basically allows you to match inputs, the functions and case statements, based off of constant values in the input. So this is one of the biggest things with the message-based communication. It makes it dirt easy to add. Like you basically would add the name of your packet or message inside of a tuple, which you can see right here. This is a tuple. You add the name of that packet, and then you can include data within that. So here's an example of it. So we have two functions. Handles, both of them are named handle stuff, and both of them have the exact same structure of input or number of inputs inside of it. The only difference between them is that this one has an atom called stuff, the other one has an atom called other stuff. So if we call this function right here with stuff and 1, it would run this function. That's pretty much just because of the fact that we are defining that if this is constant value stuff, then you run this function. And same thing over here, we have other stuff. So because of the fact that this is constant and this is a constant, it will match them and realize, okay, I need to run this function. And how does this all really relate to Nevermore? So our backend heavily relies on Elixir's features, quite obviously because it runs on Elixir. This allows for our FMS to be highly concurrent and fault tolerant to different attacks, or more importantly, bugs. And let's go ahead and talk a little bit about the actual structure of that backend. So we have what's called the field GenServers. These are the GenServers that are created in order to manage the actual field and in order to manage the different driver stations that connect to the field or to the FMS. So these 4 files right here are the most important parts. The driver station is a GenServer that talks about, the driver station is basically is a GenServer that is created by the field whenever there's a TCP socket created. The field is just the GenServer that would be created whenever you start up the actual FMS computer and whenever it starts up the application. And then the enums and timing are simply just a bunch of defined constants that are used within both of those. So how does the field first get created? So whenever the FMS starts up, as said earlier, it will create what's known as it will create the GenServer, but it also creates what's known as a dynamic supervisor. So that's another concept within Elixir, and that if your GenServer goes down, how does it restart itself? So you have what's called supervisors. Supervisors will restart a GenServer if it goes down, and that would be basically allow for it to reset itself, and you don't have to restart the entire machine or anything. It just gets done instantly. And a dynamic supervisor, you can think of it as basically a linked list when compared to an array. The array would be a supervisor. You define the amount of stuff inside of it in the beginning, while a dynamic supervisor, you can add more GenServers they can watch afterwards. So this starts a TCP listener on port 1750, and it opens a UDP listener on port 1160 on FMS. The first thing that will happen, well, first off, the FMS is fully ready for connection to that point, but then this GenServer will then create a driver station GenServer whenever it receives a TCP connection. So, sorry, can't really read this. All right, so it creates a TCP socket to the FMS, and then identifies itself with its team number as the first packet. Then it does a little challenge the FRC created, the first created, or the people who wrote the FMS. And then it sends a UDP message every 500 milliseconds to the FMS from the driver station. And it also is able to receive a message every 500 milliseconds. So the driver station GenServer, it literally just controls the TCP socket of the driver station. That's pretty much what its entire job is. And if the GenServer crashes, the TCP socket closes, and that actually causes the driver station to no longer be sending things to the FMS. And because of that, if one team were to have issues or to go down, it would not cause like the entire thing to crash, or more importantly, it would not cause the FMS to crash. And if the FMS were to crash, everybody on the field actually would stay enabled throughout that, because the fact that it's only whenever the FMS is actively connected to the driver station is it able to control the driver stations. And the FDA later on could figure out whether or not it needs to be replayed or not, but that's up to them. So we can go ahead and talk about the GraphQL API that implements our control of the field. So why only have an API? The first one uses actually just a C#, or it's a C++ application that has an interface on Windows. But we only have an API, so how would you use it? Well, we want to allow anybody to create a front end for our FMS. On top of that, we want to make it a possibility for anybody to actually scrape data during events from our FMS to know what's going on and what events are coming up. This makes it a lot easier to create a really good looking front end. And on top of that, we no longer would have to have like weird things like what the first one used was SignalR, which is event bus pretty much. And that's how a lot of the dashboards and stuff like that would get their information, which is a little bit finicky, and it's okay, but it's not my favorite thing. So our Elixir implementation uses what's known as Absinthe and Phoenix. So Absinthe is a GraphQL engine that parses and handles the GraphQL queries, which are pretty much similar to REST. However, it's built on top of that to be a lot easier and to only return the data that you want. And then Phoenix runs the actual HTTP server that then passes these queries onto Absinthe for parsing and running. And we can go ahead and just quickly talk about a database. It's not that interesting, but it's just a PostgreSQL server that we connect to using the Ecto ORM, or the object relational mapping. And it just contains the schedules, teams, matches, match penalties, and most importantly, the actual events of the entire game. So for example, whenever somebody scores, it gets logged in there. So you could think of it similar to a time series database, except for we don't want to start a time series database, so we just put it into PostgreSQL. So it's demonstration time. We're going to go ahead and quickly switch to our phone to show a demonstration of our FMS working. We got plenty of time left for it, so I'll mute myself here. Was I muted this entire time?
You were not, no.
Okay. Why in the world did it tell me I was muted here? You could actually hear me the entire time?
Yeah, you were.
All right, Cisco WebEx is really weird. It just told me that I was muted this entire time.
Oh, that might have been me, actually. Let me check.
Oh.
But yeah, don't worry. You were not muted the entire presentation. You are good.
Good. That was about to be worse than school online, but we'll go ahead and switch over to a phone to show this. All right, can you guys hear us now?
Yes, I'm going to be transferring share permissions to the phone now. So
Got it. All right. Can you turn down the volume on that? All right. So we'll go ahead and start up our video here. And if you could just show the video we're showing.
yeah, you are good. The video showed.
All right, we'll have Nathan explain what's going on here.
Okay.
Yep.
Okay. So here is our hardware. So the FMS that or the stuff that we are setting up for Nevermore FMS uses hardware by a company called Ubiquity. Now, as everything is going to be open source, both the hardware and the software, if someone wants to build a version of Nevermore with their own hardware, like Cisco or another company, they can. And there will be documentation on our GitHub page for that. But as for the hardware we're using here, this is our core switch here. And this is what connects essentially all of the other devices on the field. Here's our router, and that is what that connects just directly to the core switch, and that manages things like VLANs and firewalls and other things. And then lastly, we have our two Alliance switches over here. This is the blue one and this is the red one. And again, those just connect directly back to the core switch. Obviously, on an actual field, these would be at the two opposite ends of the field. But just for demonstration purposes, we have them all here. And lastly, we have our access point, and that's what gives robots communication to the field. So quickly, we'll go over to our driver station over here. So if anyone here is not familiar with the FIRST Robotics competition in general, all teams use this driver station program here at the bottom, and this is a program provided to all teams by FIRST and by National Instruments, and that is what connects teams to their robots. And we kind of just talked about this earlier, but whenever teams are just using their robot on their own, they connect directly to their robot. During an actual FIRST competition, the driver station gets connected via Ethernet to the FMS hardware, and the robot connects to that hardware as well. They don't get direct connection to each other. So if we go ahead and plug in our driver station, if you come over here, you'll see the driver station will register that FMS is connected. And this is, again, just to reiterate, this program here is made by FIRST, and the FMS is connecting to is our Nevermore FMS. So real quickly, here's a brief look at the GraphQL API. Obviously, in a final version of the FMS, there will be a full graphical user interface, but this is just the API like Chase talked about earlier. So if we can go ahead and go back to the directory. So if we go ahead and start the field like a normal FRC event, we'll see that it starts off by going into auto, and then it has the timer and all other game data associated with a regular FIRST Robotics competition event. This is going to count down and replicate just like you were at an event. And then obviously we can control our robot here. And this is being controlled through all of the FMS hardware, not a direct connection from the team's driver station to the robot.
Yeah, you could see that right there because it's FMS connected. And that's pretty much for it for the demo. It includes VLANs and everything, which means that you're actually not able to communicate with anybody else on the network. and on top of that, we're able to detect which station you're in, and we can tell people which station you're supposed to go to, which is what they do on the official field. So we'll go ahead and go switch back to our regular computer in order for us to do a Q&A.
Oh, there's a few more.
All right, your computer is getting share privileges again.
All right, wait. Okay, so let's just quickly talk about future uses for our Nevermore FMS. So Roboticon. So the Nevermore FMS will be used at Roboticon 2020, which is an off-season event in Tampa Bay, which is put on by our nonprofit sponsor, the Foundation for Community-Driven Innovation. And also, our Nevermore FMS is going to integrate with one of our other team's projects, Roboticon Live, which is not something we're talking about here, but the general idea is it's a platform made to, with one of the main intentions is to allow for events to happen even during COVID. So we can have minimal people at venues and still have the ability to look at what's happening live from home, and to have one event being run through multiple venues, which is currently not possible with the way that First has implemented their FMS on their website. And there's a little template for Roboticon there. And so where we're at and what we have coming. So the FMS backend is done, like we just demonstrated. We're still wanting to do an external code review, and we're also looking into a major refactor to help with readability and just general optimizations. All of the networking hardware is integrated, as we just demonstrated, but we're still working on the front end. Our front end that we're going to make specifically for Nevermore FMS is going to use React.js. But again, anyone can come along and make their own front end to serve their own needs. And the hardware, as in stuff like sensors and lights and that sort of thing, is currently in development by other members of our team. And that's going to be using a modular system to allow for easy changes between seasons and games. And so how can any team get involved? So like we said earlier, all of our code is open source. And you can look at it at that GitHub link. And so because it's open source, anyone can look at the code and learn from it and sort of gain an understanding of it, and they can help contribute back to it. If anyone is in programming and wants to get involved, these are some things that we're looking for, which is unit tests and code reviewers. And so that's the main part of the Nevermore FMS and how we're developing it. So I think we go into questions now. Jason?
Yes, so anyone who has questions, please put them in the Q&A and presenters will be able to answer them.
Uh-oh. Are we not able to see this again? Oh, there it is.
Yeah, so you guys got a question in already. What were some of the biggest challenges you came across when developing this?
Yeah, sure. One of the biggest challenges really was attempting to get it working in the first place. So the protocol is very, very finicky in the way that you do it, in which you have to order everything correctly. So you have to TCP socket first, then you have to send your actual team number, then you have to send your, then you have to connect to UDP. You have to make sure you're sending the packets every 500 milliseconds. Luckily, FRC teacher had already documented a decent amount of this. However, we did have to do a lot of trial and error in order to get it working. And we found a couple of little bugs that we had to work around with it. Yeah, sure, I can go back to GenServer Example a little bit later. And have you done much testing of simulated robots connected to your FMS? No, we do not really do simulated robot testing, mostly due to the fact that it's not exactly the robot that connects to the FMS, it's the driver station connects to the FMS. And because of that, we really can test it anywhere we want, and we can see what it's doing and what it's telling the actual driver station to do. Additionally, driver station actually has great logs, so we can look through the logs to see what was happening during that time, when it got enabled, when it was disabled, and also when it was sending the packets, which is pretty good, to be honest. What were the cons of the old closed source system? So first off, oh, you talked about? Yeah, we'll let Nathan talk.
So one of the main things, in my opinion, is that The FMS that FIRST has produced is something that's, shows production level code being used. And yet it's one of the things that teams can't look at. They can't look at the code. They can't learn from it. They can't interact with it. It's something that FIRST says exists and then it's used, but teams don't really use it on a regular basis. And I think that's sort of a lost opportunity because you get, it's something that's being used to ensure safety and to run large events. And that's something that I think teams should be able to look at and, learn from and gain experience from. And so, that's one of the main things here is that being open source allows teams to look at it and to learn from it and mainly to make contributions for the community to help contribute back to this thing that helps run all FIRST events or all FIRST robotics competition events rather. And so that was one of the main cons. And also we improved other things such as the structure of the FMS that FIRST provides. With using Elixir, for example, ours ends up being extremely fault tolerant. And as we kind of mentioned, the interfaces for the FMS is essentially one desktop computer program, whereas ours is all web-based, so it can be accessed from any number of computers or on tablets and that sort of thing.
And also, I guess the mock driver station that can be instantiated during a simulation. So, really, you can start up the driver station at any time, so there's really no need to simulate it. It just won't connect to a robot. But because the fact that it logs everything, we can actually see what the FMS was telling it at the time. And it's really just a regular FRC concept at that point, which would be disabled, enabled, whether or not it's e-stopped, whether or not it has a what the actual packets are saying. Actually, it also includes. It's actually quite in depth. And that's about it.
So does anyone have any more questions? Please put them in the Q&A.
All right, and for right now, I'll go back to that GenServer that somebody asked about. So if I go all the way back here. Oh, wait, it's lower 34.
No,
Wait, is it?
It's way back.
Oh yeah, this is after this field gen service. There it is. All right, there you go. Do you have any questions about it? You could just put it in the Q&A.
You pull up with it.
Yeah, I can't pull up Q&A, so if you could just go ahead and tell me whatever you have to put in Q&A.
Yeah, sounds good. So So if we're ever asked about the GenServer example, do you have any questions about that? Or does anyone have any more questions that the presenters would be able to answer? All right, so did you guys say what language you were using and why that language?
Yes, we use back here where I explain it. Elixir. So Elixir runs on the Erlang virtual machine. It's similar to how Kotlin runs on Java. It's just a very good language that allows for fault tolerance, and it's similar to Ruby, and it's a functional programming language without as much dynamic. But What? And yeah. Yeah, if you want to know more about Elixir, I recommend you look it up. Their website, elixir-lang.org, has a lot better documentation than what I probably could say. And it's very in-depth. It's a very cool language based off ERLang. Virtual machine, specifically.
Are you able to pull up the question screen here?
No, I can't. It's weird. Whenever you're sharing, you have to actually like disable and re-enable the Q&A to see it.
I can do that again, actually.
If you can, then I can see it.
There we go.
There we go.
You guys, yeah.
You should go to home. There you go.
All right. Looks to me like there's not really any more questions right now.
All right. So, does anyone have any more questions? Any at all? Yes.
I just don't need to go.
Yes.
Okay. We're not sure if
That's what.
sure if that is tested or if it's after tested.
Does he need anything further than from us? Are we good? I think we're done.
Want me to just go back and like say it?
Oh, let's check. Ask him if he's.
So I'm not seeing any more questions here.
All right. So,
Yeah, so thank you everyone who came to watch the presentation. Again, you can, if anyone wants to get involved, our GitHub page is very, very slowly here. There you go. Okay, so that is our GitHub page, and that's where you can see all of the code for this, and you can read it and get involved and sort of learn from it, and also submit code back to us. Yeah, thank you everyone for coming and for your interest.
all right. So with that, I would like to once again thank our presenters for contributing to this event, and I'm going to stop the recording now.